Hi everyone, hope you're all doing well. We press forward in our review of the homework. We're now on to chapter section 7.4, Vectors in 3D. This video series will be a bit different. So I've already completed all the problems and I'm going to be taking you through my thought process in all of them. Now, there's benefits and cons, I feel like, to this approach. How I was doing it before, which I will still be doing, I'm just experimenting right now to see some of your feedback. The pros of how I did it before, I guess, were you could see me live making mistakes. Well, as for this one, you see my fully fleshed out ideas right there on the spot in a pretty compact and neat form. So, yeah, pros and cons to both, but I guess we'll adapt our way through the semester. And you can let me know with your feedback if you prefer one way or the other. All right, so let's jump straight into it. So we're starting off with question 3 here. Draw each position vector. So for 3A, all you have to do is you have to create your 3D Cartesian grid now with the plus x, plus y, and plus z axis labeled for, and then the minus x and minus y and minus z axes. And then use tick marks to indicate how far along each axis you're going. So for this case, what I did here was for -1, 5, 2, I went -1, so that's backwards in the x, which you can see right here. Then I went 5 along y, so 1, 2, 3, 4, 5. And then I went 2 down, which is in the negative z direction. All right? And the same process similarly holds for part B. Okay. Question 4, find the exact magnitude of each position vector in question 3. This is quite easy. It's the same way how you would find the magnitude for 2D position vectors. All you're doing is you're using the Pythagorean theorem. In this case, we have 3 components to work with instead of 2. So for 4a, I just took my vector v here, -1 squared plus 5 squared plus -2 squared. That's all equal to square root 30. And for c, for 3, so 4c corresponds to question 3c, I did 0 squared plus -2 squared plus -4 squared, and I get square root 20. That's right here. All right? So same deal, just using the Pythagorean theorem. Okay, moving on. So now we have question 5. Express each vector as a sum of the vectors I, j, and k. So I did questions 5 and c for this one. So let's look at the vectors. We have 3, -5, 2. This is going to be 3 lots of I, and it's going to be minus 5 lots of j, and plus 2 lots of k. All right? That indicates how much we have to go along each of those unit vectors. So we're creating linear combinations out of I, j, and k. Okay, for 5c, same deal. I need 3 lots, sorry. Oh, that's actually wrong. I'm glad I spotted that. That should be a 5, not a 3. So I need 5 lots of I, and I don't need any lots of j, the j vector, but I do need 7 lots of k. And that completes 5. Okay, moving on to 6. Express each vector in the form of ABC. So now we're doing the reverse process. We have it expressed as a linear combination of I, j, and k. And we're now re-expressing it in its compact Cartesian form. So we have 3. So I did A and C for this one as well. So we have 3i plus 8j. Now, remember, we're working in 3D for these questions. So that's going to be 3, 8. But because k is missing, we still have to put a component for k because we're working in 3D. So it's 0 in this case. And then C, we have 7 minus 4, 9. Okay, perfect. Question now 7. Are the vectors u and v collinear? So, what does it mean to be collinear? It means, does there exist some lambda in R such that u is equal to lambda v? Now, that looks like a complicated statement, I know. But to boil it down, all it's asking is one of the vectors a scalar multiple of the other? That's all it means. That's all this statement means. So that's what I'm checking. I'm checking to see if either one of them is a scalar multiple of the other. So how I like to do these questions is I like to write them in rows like this. So I wrote u here and v here, and then I'm just comparing their components. So then I realized that each component of v was just times -2 of all the u components. So they are collinear, that means, right? V is a scalar multiple of u. In fact, this is what I wrote. I wrote that -2 times the vector u, exactly here, would give me v. So u and v are collinear because there exists some scalar out there that when I multiply u by it, it gives me v. Or vice versa. I could also use -1/2 v and get u, right? So they're collinear. Good. All right, moving on. All right, so determine all unit vectors collinear with 4, 1, -7. So there's only two, always like there will always be two unit vectors collinear with any vector. That'll be 1 over the magnitude of v with v on top, and the other one will be the negative guy. So the parallel and anti-parallel, I guess you could think of it like that. So it's the same procedure for these questions. If you're asked to determine all unit vectors collinear, you're just going to have to find the magnitude of your vector, 1 over v, 1 of the modulus of v. Modulus just means magnitude again. So that's square root of 66, and you can find that very easily by doing 4 squared plus 1 squared plus 7 squared. And that gives you, just to check, square root of 66. So that's where I got that square root of 66 from. Okay, so you have two unit vectors that will be collinear. One is the positive guy, and the other is the negative guy. That's u2. I called them u1 and u2, u for standing for unit. Okay, perfect. Question 9 asks us, find a and b such that u and v are collinear. Okay, so again, I'm looking to make it so that u and v, the only difference between them is of a scalar. So some scalar multiplying either u or v will give me the other one. Okay, so I'm going to line them up again, row by row. And what I notice is that if I want to get 12 from 3, I multiply by 4. Right? I multiply by 4 here. If I want to get... So that's the key I noticed, right? If I want to get 12, I had to multiply by 4. Meaning, b is just going to be taking 6 and multiplying that by 4. Okay? That means b must be 24. Okay? So then finding a, again, the difference is by a scalar multiple. Instead of multiplying by 4, I'm going to divide by 4, or multiply by 1/4. So, yeah, to get a then is a will be equal to -2. Okay, so the difference between u and v is just that of multiplication by a scalar. That's all this question is asking you to recognize. So then u is -2, 3, 6, and v is -8, 12, 24. Okay, for part B, you're given it as a linear combination of I, j, and k, which I first transformed. So I transformed u to be a2, 0. Again, even though it's missing its k unit vector, we have to assume it's 0 if it's not there, because we're working in 3D. And then v is this guy, -3 and -6 minus b. Okay? So what do I notice? I notice the pattern that to get -6 from 2, I had to multiply by -3. So that means all the other ones have to be multiplied by -3 for me to get v, the components of v. So 0 times -3, well, that's just still going to be 0, so that means b is equal to 0. Okay, and to go the other way around to find a, I divide by -3, which means that a must be 1. Okay, because -3 divided by -3 is just 1. So that means u is 1, 2, 0, and v is -3, -6, 0. Perfect, good. Question 10. So from question 10, I did A and C. It's asking us to draw the vector AB joining each pair of points, then write the vector in the form x, y, z. Okay, so I drew the points on the Cartesian grid just using tick marks to indicate where they lie, and then I joined them by a vector. Not too difficult. Your diagram might look a bit different. It's, as Ms. Kradic discussed, our diagrams for 3D Cartesian vectors can look a bit funky always. Okay, and for C, same procedure. Just use tick marks to indicate where the points lie and then connect the 2 points with the vector, joining them. Okay. 11 asks us to determine the exact magnitude of each vector in question 10. So this one, similar to how we did it for 2D vectors, 2D position vectors, first, if I want the vector AB, I'm subtracting the x-coordinates of B from the x-coordinates of A, subtracting the y-coordinates of B from the y-coordinates of A, subtracting the z-coordinates of B from the z-coordinates of A. Because I want the vector AB, it's always in the reverse. So I get 3, 6, -2, because I know the 2 points that they were listed in part question 10. And then I just find the magnitude as usual using the Pythagorean theorem. And the similar procedure holds for part C. Okay, just using Pythagorean theorem at the end to find the magnitude. Question 12, the initial point of a vector mn is m -5, 0, 3. Determine the coordinates of the terminal point n. Okay. So I don't know why I wrote D. Oh, that's interesting. I guess I did 13 instead of 12. So let me actually scratch that. They're both very similar problems anyway. It doesn't really matter. But let me change that. Okay, so the terminal point of a vector DE is, so you're given the point E, and you're asked to determine the coordinates of point D. Okay, so DE, that comes from the subtraction of x coordinates, the subtraction of y coordinates, and the subtraction of z coordinates. And remembering, you're always subtracting the e's. The E comes first, and then the D's, respective D components. Okay, and we're actually given what the vector DE is, -4, 2, 6, so I wrote that here. Okay, and then from our previous formula, I just plugged in what I know for point E. Point E is 3, 3, 1. So that's what I plugged in here. That's 3, that's 3, and that's 1. Okay, and now I'm asked to find dx, dy, and dz. That's really simple, because now what you can do is you can set up 3 equations based off of having component equality. So note the word I used there, component. Each component must be equal to, so -3 minus dx, that's equal to -4, right? 3 minus dy is going to be equal to 2, and then 1 minus dz will be equal to 6. Okay, and then solving each equation, so dx is 7, dy is 1, and dz is -5. And that gives me the coordinates of the point D, which I guess I could write down. It's 7, 1, -5. Beautiful. Nice. All right, moving on. Questions 15, 16, and 17. All right, so 15. So given the vectors A, -4, 1, 7, B, 2, 0, -3, and C, 1, -1, 5, simplify each vector expression. So for this one, I did A, C, E, and G. So the first one is just doing a scalar multiple. I'm just taking 7 and multiplying it by the vector A. Pretty simple. You just kind of distribute this 7 into each component. -28, 7, 49 is the vector you get. B plus C plus A. So for this one, you can actually add them in any way you like because vector addition is associative. So I could have chosen to do C plus A first. I could have chosen to do B plus C first. It doesn't really matter because vector addition is associative. So I took my vectors, 2, 0, -3, 1, -1, 5, plus -4, 1, 7. So I guess I probably chose to do B plus C first. So that'd be I'm doing component addition, and then the result of that, I'm going to add it with -4, 1, 7, which is vector A. And then I get my vector -1, 0, 9 out. Okay, good. All right, so question E. I'm taking some linear combination now. So I'm taking 3A minus 2B plus 4C. Okay, so I take the 3, times it by vector A, minus 2 times vector B, plus 4 times vector C. So again, I am distributing each of these scalars into the components first. That's how you scalar multiply Cartesian vectors. Okay, kind of like distributing in a sense, you can think of it. And then I get -12, 3, 21, minus 4, 0, -6, plus 4, -4, 20. And then I added these guys first, but again, it really does not matter. Vector addition is associative. You could have done it any way you like. I don't need to put brackets there anymore. And then, yeah, just do component-wise addition. Beautiful. G. B dot A plus C. Okay, so this one, it matters what we do first, and we're also told what to do first in a sense as well. We're told to do A plus C first. So that's what I did. I did component-wise addition to get the Cartesian resultant, which is -4 plus 1, that's -3, 1 plus -1, that's 0, 7 plus 5, that's 12. So the result I get is -3, 0, 12. And then I'm dotting it with 2, 0, -3. So it's going to be 2 times now I'm doing component-wise multiplication and then adding all those up. So 2 times -3 plus 0 times 0 plus -3 times 12. And the final answer I get is -42. Okay. So you're told what to do in this case first, the brackets first, right? So you're doing A plus C, then you're dotting that resultant with B. Good. Question 16, determine the angle between the vectors. Okay, so the angle between the vectors, very simple formula for this. We're equating, this in a sense is the Cartesian dot product. Oh. We equate the Cartesian dot product with the geometric dot product. Okay, and then we just isolate for theta. So bringing cos theta over to one side, I get g dot h, all divided by the magnitude of g times the magnitude of h. Okay, now I found the magnitudes here. So the vector g is 6, 1, 2, h is -5, 3, 6. I found the magnitudes using the Pythagorean theorem right here. And then I inputted that. Now, mind you, I didn't do g dot h explicitly here, but I can show it to you on the side. It's going to be 6 times -5 plus 1 times 3 plus 2 times 6. which equals, I have it right there, but I'll just do it again. 6 times negative 5 plus 1 times 3 plus 2 times 6, you get negative 15. Lovely, and that's what I see here. Then I had the magnitudes, and then I'm just isolating for theta using the cosine inverse. And I get 106.26 degrees. Perfect. Okay, final question. Question 17 asks us determine two vectors that are orthogonal to each vector. So I only did part A here. I just want to go back and actually note one thing for 16. So I think I mentioned this in the last video series, but when finding the angle between any two vectors, always resort to the dot product. Resort to the dot product. Do not use the cross product, which is another way to multiply two vectors together. Always use the dot product. It's much simpler, and it's I guess that's the only note I have. Now, so moving on to 17. So it's asking us to determine two vectors that are orthogonal to each vector. So I'm only doing part A. So we have E equals 3, negative 1, 4. And the goal is find two vectors, which I'm calling U1 and U2. S dot T is a mathematician's lazy way of saying such that E is perpendicular to U1 and E is perpendicular to U2. So just to reiterate, find two vectors, U1 and U2, such that E1 is perpendicular to U1 and E is perpendicular to U2. That's what the question is asking. But we can boil that condition down to something we know, because that if they're perpendicular, that means E dot U1 is equal to 0 and E dot U2 is equal to 0. Should put vector symbols here. And then I wrote those conditions down right here as 1 and 2. So my notation is a bit sloppy, but sometimes I feel like this is a physicist notation. So we have 3u1x minus u1y plus 4u1z equals 0. I'm just dotting the two vectors. I'm dotting E with u1 and I'm dotting E with u2. And I'm calling their components what they are, x, y, z respectively. So that equals 0. And we have another statement that 3u2x minus u2y plus 4u2z equals 0. Now I'm just finding two vectors. So u1 and u2. So to find u1, what I did is I automatically made the first guy u1x 0. So then I figured out, okay, now I need to find a combination that will make u minus u1y plus 4u1z equal to 0. And what I chose was, if I make this guy 4 and this guy 1, then I'll have minus 4 plus 4 times 1, which is 4. So minus 4 plus 4, 0. So that's why I chose u1 is 0, 4, 1. For u2, I made the second guy 0. Not the second guy. The third guy 0. Okay. So now I need a combination of u2x and u2y such that 3u2x minus u2y equals 0. So I chose u2x to be 1 and then this guy to be 3, which also makes sense because now 3 times 1 minus 3, so 3 times 1 is just 3, so 3 minus 3 is 0. The dot product equals 0. Left-hand side, right-hand side are both equal, and I'm good to go. So yeah, for these questions, just choose which component you're going to make 0. That's usually the easiest way. And then set the other two equal. Find the other two components, x and y, or x and z, or y and z, whatever you do, such that it's equal to 0 on the right-hand side as well as on the left-hand side. Okay? That's good. And that's the end of this video series. I'm only making one video. If you want to leave a comment, if you like this, prefer this method, or prefer the latter way, at least this way seems much shorter, but it's up to you guys at the end of the day. Thanks, guys. Have a good day.